Hello, and welcome to this edition of Math Teacher to Go. My name is Pat Doobie, and today we'll be talking about composite functions, when you take functions and nest them inside of each other, or find values of one function and put them into another. We'll start with a review of domain and function notation, and then we will move into the composite function material. So to find the domain of a function, we're going to find the domain, we're going to combine functions using the algebra of functions, form composite functions, and then find domains for those composite functions, and then write functions as compositions of two functions. So function notation is a set of instructions for finding y. You should be very familiar with this. If not, take a look at these notes. But x is basically a placeholder. Whatever is in the parentheses shows up here. It says to find y, when you have x, put x in 3 times x squared plus 2x minus 8. So I like to put parentheses around all the x's, and then when I replace the x with, let's say, a 5, every place I have a parenthesis, I'm replacing with a 5. So I know to square this 5. I know to multiply this 5 by 2. Okay. So here's another example. We put in f of 2. You can see in pink that I have replaced all the x's with 2's. That you should be very familiar with by now. Now the other thing we can do, and we looked at this in a little different context when we did function shifting, is we don't have to just put numbers in. That's what becomes kind of new here. When if I want to find f of x plus 3, we learned that would shift f of x3 to the left if I had the graph or the points. But what if we had an equation for f of x? How would we find the equation for f of x plus 3? Every place I used to have an x, I put an x plus 3. You have to be really careful when you simplify this, though, because people tend not to square binomials correctly here. X plus 3 squared is not x squared plus 3 squared. It's x squared plus 6x plus 9. You have to multiply out the binomials. You may have learned to do that by foiling or with a grid, but you have a middle term there. And then you distribute the 2 to get the 2x plus 6. Then you distribute the 3 and combine like terms, and this is your final simplified f of x plus 3. And you can see its domain is the same as the domain of the original function because it's still a polynomial. So the domain of functions, we need to know the domain of functions we're working with, because the domain of the function that goes inside another function it becomes a restriction, as well as the domain of whatever new function that creates. These are the same slides we saw before when we did domain. Sometimes domain is restricted. At the bottom you can see you're told what the domain is, but most of the time you have to be aware of what issues cause trouble when evaluating a function. Here are the rules. Division by 0 is not allowed. An even root of a negative number is not allowed. Polynomials have a domain of all real numbers. So if you don't have division by 0 or an even root in your problem, your domain is all real numbers. You have to look for division by 0 when you have a variable and a denominator. You have to find out what would make that expression, the denominator, equal to 0, and exclude it. And here is an example. I have a denominator of x minus 4. That can't be 0. So I find out what x would cause that to be 0 and say it can't be that, so x cannot be 4. Since x cannot be 4, here's how I leave that out in interval notation. If you're not required to do interval notation, this is fine, or you could say any number except 4. I'm moving along rather quickly through this because this should be familiar. When you have an even root, and this is an even root because we don't write it, but there's an understood 2 in the index. Other even roots would be 4th roots, 6th roots, any even number in the index. Because that means give me a number that you multiply by itself an even number of times and it turns out to be what's inside. If what's inside is negative and you multiply it an even number of times, it's not possible in the real number system. When we talk about domain, we are talking about the real number system. So here we know x plus 5 must be 0. Square root of 0 is okay because 0 times 0 is 0. So you take what's inside the square root and you write an inequality with it greater than or equal to 0. And you solve it. And this gives us x greater than or equal to 5. I actually have this written incorrectly in interval notation. X greater than or equal to 5 should be 5, infinity. So fix that in your notes. And let's move on. I want to get past domain here. Sometimes you can have more than one restriction. I have two things going on. I have an issue where this has to be greater than or equal to 0 inside the square root, and this bottom here cannot be equal to 0. So I will solve for both of those cases and exclude the numbers that would violate those rules. Okay, and that's what I just said. Inside square root must be positive, denominator cannot be 0. If you solve each of these, you get a combination of x has to be greater than or equal to negative 2, but it cannot be 7. If I was simply going to write x greater than or equal to negative 2, that would give me negative 2, infinity. But I need to leave out the 7 because the 7 shows up somewhere in the middle of this interval here. So how I do that is I go negative 2 up to the 7, and then I go from 7 to infinity. And that will combine the two conditions. So sometimes you have to combine your answers. You have to think about what you have to do with that before you can state what the domain is. So some of the ways, now let's get into a little bit head towards function composition. You can add functions. You've done this for a long time. You called it combining like terms, basically, or subtracting them, or multiplying or dividing. If you're told to add two functions, it really is just combining the like terms of each function and turning it into one new function. So if we have f of x is 3x squared plus 2x minus 8, and g of x is x plus 3, and I am told find f plus g. Now they kind of leave the of x out. They just write f plus g. That means add the functions named f, the function named f with the function named g. There's my function f. There's my function g. The adding makes it easy. I can just remove the parentheses. 3x squared here. There's a 3x squared. There isn't a like term over here. Here there's a 2x. There is a like term here. 2x plus x gives me the 3x. And negative 8 plus 3 gives me the negative 5. So what if I subtract them? This is, you're going to say, well, it's the same thing. Well, sort of. You have to be really careful, though, because you have to remember that g of x is this whole thing. And you must put this in parentheses when you subtract. I would suggest to be in the habit of always putting your functions in parentheses before you do an arithmetic operation on them. The reason is, if I don't put this in parentheses, I subtract the x and I add the 3. I want to subtract the whole thing, which means I want to subtract an x, and then I want to subtract a 3. I have to distribute that negative 1 through. There is another way to look at this also. Let me clear these strokes. So when I do the subtraction, I have a 3x squared, and I have nothing to subtract over here. That x can't be subtracted, so I don't do that. So the 3x squared just gets written down. Then I look at the 2x, and I have an x in my subtracted function. 2x minus x shows up here when I distribute, but 2x minus x gives me positive x. Negative 8 minus 3 gives me negative 11. So you can either do this by distributing the negative and turning that to a negative x minus 3 and then combining like terms, or subtract like terms. Start with the left function and see what is like in the right function and do subtraction a term at a time. Whichever gives you more accuracy is the way you should do this. Do not be that person that always forgets about the negative in front of the parentheses. So what if we're asked to multiply? And to multiply, we write two expressions right next to each other. That's multiplication. fg would be f times g. So I'm working with these same two functions, f and g. And then it's f of x times g of x. So I literally do that. And the way you multiply this is you do 3x cubed times x. 3x squared times x plus 3x squared times 3. Then do the 2x times x, 2x times 3, and then go back to the negative 8 times x, and they give 8 times 3, and add them up. So that came from multiplying by the 3x squared, that came from multiplying by the 2x, and that came from multiplying by the negative 8. When you combine like terms, you get this. Now there is another way I like to set this up, and let me see if it's on the next slide. I should have looked ahead of time. Okay. I like to set this up in a grid. If I have, let me not do f over g right now, let me do f times g. If I have a trinomial times a binomial, I like to set this up like this. I'm going to write my trinomial, let me erase that, sorry. So I'm going to make a grid. A box. I'm going to make boxes. Some people call this doing it by boxes. And I have 3 terms by 2 terms, so I need 3 by 2 grid, either 3 columns, 2 rows, or 3 rows and 2 columns. And in the grid, above the grid, I put the first polynomial, 2x minus 8. I write a term of that above each column, and I include the signs. And then going down the side, I'll write what I'm multiplying by. And inside each square now, oops, sorry, I just scribbled. Inside each square, right here, right there, I'm going to put 3x squared times x. Those two multiplied together, and that'll give me 3x cubed. Then I put 2x times x is 2x squared. I'm going whatever intersects. So negative 8 is the column, x is the row. This becomes negative 8x. 3x squared here. 3x squared is the column. 3 is the row. 9x squared. Here 2x is the column. 3 is the row. 6x. And here negative 8 is the column. And 3 is the row, so I get negative 24. And when I add all those up, indeed I can see there's my 11x squared. Negative 8x plus 6x will give me the negative 2x. I get the same thing, but I like to organize it this way. You'll see me do this more in class also. Okay, so the other thing, we've added, we've subtracted, we've multiplied, and you've done enough math now that you should know the next thing is we divide. So if I'm making a fraction, that's a division. So I'm doing f divided by g. For all you're going to do for right now is set this up and tell me the domain. You're not actually going to divide the 3x squared plus 2x minus 8 divided by x plus 3. That comes a little later. But for now, you're just going to set this up. So I set up my fraction. And now I have to look, because my domain of each of these was all real numbers, and that's an abbreviation for all real numbers. But now when I put the g of x in the bottom, I create a domain issue. So going into making a function out of 2 functions, I didn't have any domain restrictions, but when I'm done, I do. So x plus 3 can't be 0, so x cannot be negative 3, because if I put in a negative 3 here, I will be dividing by 0, and that's a terrible thing to do. All right, so adding, subtracting, multiplying, dividing, very straightforward. Don't get all tangled up in that. You'll make silly mistakes, but how to start the problem, if that's an issue, look back at these notes and it should be pretty straightforward. Now, let's take our same two functions and do something different. We're going to compose the function by putting one inside the other. So I am going to take g of 2 and put it inside of function f. So in math, we work from the inside out in parentheses. The most inside thing I have is a 2. Okay, so there's nothing to do to that. There's no operation to perform on it, so I move out a step to g of 2. I can find a number for g of 2. g of 2 is 5. So I replace this g of 2 with a 5 because that's what it's equivalent to. So I am now finding f of 5. Now I can find f of 5. I can put that into function f and find f of 5. So you take it a step at a time. Find the inner function. When you have a number, these are a very mechanical process. Take it a step at a time. Find the value of the innermost function and then plug that in for the variable in the outer function. So here's what I get when I find f of 5. Put 5 in each parenthesis. So the answer to f of g of 2 is 77. So when you have all numbers in these problems, and that's a 7, not a 2, sorry. When you have all numbers in these problems, you get a number for an answer. So, but what if I asked you to find instead f of g of x? Now, I start here and there's nothing to do. G of x is defined there for me. There's no evaluation to be had. So this is asking me to find f of x plus 3. I can replace g of x with x plus 3. That's what this equal sign allows me to do. It says they can be replaced by. So now I find f of x plus 3. And when I do that, it gets a little more complicated. The other thing you need to be aware of is in your text, and in most texts, f of g of x can be written this way. I like it that way because it shows you exactly what's done first, what goes inside. But most books write it as this, and most students tell me that's fog of x. It's actually not fog of x, it's f of g of x. In this one, you start with the one that's closest to the x and move backwards. I like to take, when I see things written like this, I rewrite them like this because it's much clearer to my brain what goes inside of what. Students often get them backwards when it's in this fog notation. So again, the question becomes find f of x plus 3 no matter which way you write it. Your homework and your text and anything you read will likely have it in this notation, but it means the same as this. So you must know that. And here's what happens when we find f of x plus 3. We plug in x plus 3 everywhere we had an x, and we did this on a prior slide when I reviewed function notation. Make sure you do the correct algebra with the foiling of the x plus 3 squared, and then group like terms correctly, add correctly, do all those things very carefully. So what is g of f of 2? Now the order matters. We found f of g of 2 before, and a couple slides ago we had this. We had f of g of 2. Look at the difference. F of 2 was on the inside this time. So your book will write it like this, gof of 2. But again, start with the end and work your way backwards. Start with the variable or the number given. Now because this is a number, your answer is going to be a number. You start by finding f of 2, and you find out you get 8. Then you're going to put that in, so the question now becomes find g of 8. So you're simplifying it. This looks a little easier. Once you find f of 2, the problem looks easier. So now f of 2 was 8, so now I need to find g of 8, and I've done that here because g of x was just x plus 3, so it's just 8 plus 3. So that's a couple of examples of functions within a function. You need to know how to do those very quickly. All right, the domain of functions within a function come from a couple places. If you start with a function that already has a domain restriction, you keep that domain restriction if that is the inner function. When you're done, you have to look at your result and see if there are any new domain restrictions. So only values in the domain of the inner function are included. So the inner function, if it has a restricted domain, that gets inherited by your new function. Any new x value that yields a y value for the inner function that's not in the domain of the outer function. The fancy way to say that is look at your new function and see if you've introduced any new restrictions. That's really what you have to do. So here's an example where we're going to take f of x and g of x. And f of x and g of x both have domain restrictions. If we look at f of x, we see we're dividing by an x plus 4, and that could give us a 0 in some circumstances. So for f of x, our domain is x can't be negative 4. For g of x, our domain is x cannot be 0. So if I put g of x inside of f of x, I know x can't be 0. And then I can look back and see what else I have to do for my final function for limiting the domain. So let's do this. X can't be negative 4. So this is how you would find the y's that are not included in x. I'm going to show you a different way to do it in a second. So you know x can't be 0 because you can't have 0 because of g of x being the inner function. But it's also true, if we look back at f of x, you had a x plus, whoops, somehow I've managed to go ahead a slide here. Okay, you have an x plus 4 in the denominator in f of x, so x can't be negative 4. So what the next slide is saying is because x can't be negative 4, you have to also set, and you're replacing your x's with g of x. G of x is 1 over x. So since you're replacing x in f of x with 1 over x, this is now what can't be negative 4. And you solve. So x can't be negative a fourth or 0. There is another way to look at this, and that'll be coming up next. Okay, so when I put g of x inside a function f, here's where the x was. That was x in f of x. Excuse me. So I have found that g of x cannot be 0 because you couldn't put that in for x and g of x. But there's also the restriction that x cannot be negative 1/4. And we found it in the last slide by setting 1 over x equal to negative 4 because that was excluded from f of x. But you could wait until you get to the end and you could say, okay, now this cannot be 0. 1 over x plus 4 cannot be 0 in my new function. And you solve that. And some of you are thinking solving that is a nightmare. It's not as bad as you think. 1 over x equals negative 4, or actually cannot be negative 4. Now multiply both sides by x. 1 equals, or is not equal to negative 4x because we're excluding it. And then divide by negative 4. Negative 1/4 is not equal to x. That's the other way you can do it. You can wait till the end. Exclude the domain restrictions that come from your inner function and then wait till the end and look for more. That might be easier for you to conceptualize. All right, that's the end of this edition of Math Teacher to Go. You have an assignment associated with this, and there's also another video about how to use graphs to find values of composite functions. Take care, and we'll see you next time.